Hi, and welcome to 2.1, the tangent problem. Tangent, when we talk about tangent in math, we're talking about something that touches something else. So in this case, we're going to have our function f of x, and we're going to have a line tangent to the curve f of x at a particular point. So maybe later with some time way out here, they may cross, but our focus right now is at the point x equals a. And the curves touch right there. So the graph of the function f of x and the line L, which is, the line tangent to the function f of x at the point x equals a. And the properties they have in common are, well, they share the point a and f of a, and they also share the steepness at this point. So the steepness of the line is the same as the steepness of this curve. And steepness is otherwise known as the slope. So now in calculus, we talk about the steepness of any function. Previously, we only talked about, in our algebra classes, we typically only talk about the steepness of a line. What makes a line linear is the fact that its steepness is constant. No matter where we stand on this line, it has the same steepness. But if a function is not linear, it does not have that characteristic. So no matter where we stand on this curve, as we move from left to right, the steepness changes. It's not very steep if we're standing here, but it's pretty steep if we're standing up here. So our goal is to be able to identify steepnesses at points on functions that are not linear, and tangent lines are going to help us do that. So to keep in mind, again, when we talk about a line tangent to a curve at a point, we have to understand that they share that point. That point is both on the line and on the curve. If we move a little bit to the left or a little bit to the right, they don't have those points in common. And then however steep the line is, tangent to the curve at that point, that's how steep the curve is at that point. So our goal is to be able to find equations of tangent lines and be able to then identify how steep a curve is at a point. So process by example. How are we going to do this? We're going to look at a very basic function. We're going to look at this function f of x equals x squared, and we're going to focus on the point x equals 2. Right? And we want to find the equation of the line tangent to the curve at this point. So the line is going to also go through the point 2, 4, and I know it's the point 2, 4 because it's on the function f of x equals x squared. So when I stick 2 into x squared, the output is 4. So the coordinates of this point are 2, 4, and I'm looking for the line that goes through that point and is as steep as the curve at that point. So it just touches it, it just skims it. Now this is not linear, it's curving up and it's going to get steeper as we move left to right, where this line is not. So our goal is to find the equation of this line right here. So how do we do that? Well, in order to find the equation of a line, we always need to know two things. We need to know a point on a line, which we do know the point 2, 4 is on the line, as well as the function. We need to know the steepness of this line. So that's the tricky part. So how we're going to do that is we're going to use a sequence of secant lines to approximate what's going on at that point. So remember, a secant line goes through 2 points on the curve. So I'm just going to strategic, we're always going to include this point. Actually, you don't have to, you can straddle left and right. We'll talk about that a little bit in a minute, but I'm going to look at the line that passes through this point and another point on the curve. And for simplicity, I'm going to start by looking at the point 0, 0. So my first secant line, I'm going to look at how this line behaves. It goes to the point 0, 0, which is on the curve, and also through the point 2, 4, and I want to find the equation of this line. So this will be good in helping us remember our line making skills. So we need two things. We need to know the slope of the line. So m it's the change in y, so we're going to do 4 minus 0 all over the change in x, 2 minus 0. So the slope of this first secant line is 2. Right, and we already know that the y-intercept is 0, so therefore I know that the equation of this line is y equals 2x. So that's the slope of the first secant line. I'm sorry, that's the equation of the first secant line. The slope is 2, and the y-intercept is 0. So if we go back up to this guy, we can see that the slope of the line tangent to the curve is clearly steeper than this one. So I'm going to approximate that or conclude that the slope of the tangent line must be bigger than 2. And then if we imagine this continuing like this, I can see that my y-intercept is going to fall below the x-axis, so it's going to be negative. So it's going to be negative down there. So this is a decent approximation, but 0 is kind of far from 2. So maybe we would get a better approximation if we moved closer to 2. So we're going to continue in this process. Our second secant line is going to go through the point x equals 1. If x equals 1, then y equals, well, this is the function f of x equals x squared. So just a reminder, so the output would be 1. And then this point is still going to be the point 24. And we're now going to find the slope of this secant line. So if you notice, first of all, the y-intercept is going to be negative. And it looks a lot more like this line. It's more steep as opposed to that one. So maybe this would be a better approximation because 1 is closer to 2 than 0 is. So first let's find the slope. The slope of this line, well, let me see, the coordinates of this point are 1, 1. So it's going to be 4 minus 1, the change in y over the change in x. So the slope is 3. Now I prefer to use the point slope form of a line. If you're more comfortable with y equals mx plus b, as long as you do it correctly, that's absolutely fine. I tend to use the point slope form. The point slope form is y, and I'm going to refer back to this point right here. Y minus the y value you know is the slope times x minus the x value you know. I just like it. I think it's more of a one-step process as opposed to finding b and then plugging it back in. So I get y minus 4 equals 3x minus 6, distribute, and then I get y, add 4 to both sides, 3x minus 2. So that is the equation of the second secant line. The slope of the second secant line is 3, and the y-intercept is negative 2. So that looks more like our line of interest than the first line. So how could we get a better approximation? Well, the idea is to take this secant line and move one of the, identify a point and then move this point closer and closer to that point. So instead of using 1 and 2, I'm looking to see what's happening at 2. I'm going to see what's going on at 1.5. Now this gets a little bit tricky because things are going to start getting all smudgy. But if I put 1.5 in here, it's going to give me this point right here. Now be really careful because that's not, the output is not 2. If I put 1.5 in here, it's going to be, my input is 1.5, my output is 1.5 squared, which if you do 1.5 squared, you're going to get 2.25, so it's just above 2. This is still the point 24, and I'm finding the equation of this line. So it looks very similar to this one, but it is still steeper. It's actually going to behave a lot like the line that we're looking for. So we're going to continue with the process. The slope is the change in the y values, 4 minus 1.5 squared. And I left 1.5 squared because I'm going to let my calculator do the work. 2 minus 1.5. And if you get this entered into your calculator correctly, I believe you get the slope to be 3.5. And then I'm going to go back to this point, and I'm going to do y minus the y value you know is the slope times x minus the x value you know. Y minus 4 equals 3.5x minus 7. Let's add 4 to both sides. We get y equals 3.5x, and it will be minus 3. So this line has slope of 3.5, and it has a y-intercept of negative 3. So of these three, so far this one seems to look the most like that one. So how could we even get a line that looks better, more like the one that we're looking for than this one? Well, move 1.5 even closer to 2. And I know this is tedious and extreme, but it's going to get us where we need to go. So again, we are creating a sequence of lines. We're moving our point closer and closer to the point 2,4. This is going to get really hard to see because I'm going to use 1.9. So I'm going to find the equation line, the secant line through these points. And it's so hard to even distinguish this in the tangent line, but let's find the equation of this line. So the point here, the input is 1.9, the output is 1.9 squared. And you can square it and put that number there if that makes you feel better, but I'm just going to have my calculator do all the work right here. 4 minus 1.9 squared all over the change in x, 2 minus 1.9. Now be careful, make sure you use your parentheses appropriately. I get the slope of this to be 3.9. So what we're doing is we're creeping in on this line right here, the tangent line. And this one so far looks the most like that. So let's find the equation of this line. Y minus the y value you know equals the slope 3.9 times x minus the x value you know. Now we didn't have to use 2, 4 here. We could use 1.9 and 1.9 squared. But why work with those numbers when we have these two nice numbers 2 and 4 to work with? So we get y minus 4 equals 3.9x minus 7.8. And we're going to add 4 to both sides, and we get y equals 3.9x minus 3.8, right? So now the slope of this line is 3.9, and the y-intercept is negative 3.8. So going back to our previous two, we can see how as we get closer and closer to this point 2, as we choose our second point closer and closer to 2, it's starting to look more and more like this. So the furthest I'm going to take this is by going just a little bit closer, and we're going to look at the point 1.99. So we're going to look at this point and this point, which are so super close together. When I draw the line, it just totally overlaps and we can hardly tell the difference. But let's just see how the slope behaves and how the y-intercept behaves. So let me see, let's put the points in. This is the point 2,4. This point is the point 1.99. The output is 1.99 squared because we're still on the function y equals x squared. So we have the slope is 4 minus 1.99 squared all over 2 minus 1.99. And when we pop that into our calculator, make sure you use parentheses and make sure you practice this. You get the slope to be 3.99. So the equation of the line is y minus 4 equals 3.99 times x minus 2, or y minus 4 equals 3.99x. Whoops, I didn't do that. 3.99 times 2, just because it's late. Is minus 7.98. I knew that. And y equals 3.99x minus 3.98. All right, so we start seeing a pattern here with our slopes. As we moved closer and closer, these 2 points closer and closer together, we first started with a slope of 2, then our slope went to 3, then it went to 3.5, then 3.9, and then 3.99, and our y-intercept started at 0. Then our next y-intercept was -2, then -3, then -3.8, and then -3.98. So let's make a conclusion by looking at what's going on here. 3, 3.5, 3.9, 3.99. This one behaves most like this. So I think it's fair to conclude that the slope of the line that we're looking for, what do you think if we were to use 1.999 or 1.99999, so forth and so on? Well, I can tell you that we are getting closer and closer to 4. And the y-intercept at this point is getting closer and closer to -4. So I conclude the equation of the line tangent to the curve f of x equals x squared at the point x equals 2 is y equals 4x minus 4. So this is y equals x squared. They shared this point right here, and this is the equation of the line y equals 4x minus 4. So no matter where you stand on this line, the steepness will be 4. As you walk on this curve, x squared, the steepness changes. But as soon as you hit this point, the steepness is 4. And as we continue to move to the right, it gets even steeper. So that's quite a tedious process, but I know you can handle it. So a couple of notes here. There are many ways to approach this problem. We could have chose points to the right of x equals 2 and worked towards x equals 2 from the right. So what do I mean by that? If we went back here, we could have started maybe at 3 and found the secant line between the points x equals 2 and x equals 3. And then gone to x equals 2 and 2.5, 2.1 and 2.2, so forth and so on. So we could have moved in from the right. Also, we could have straddled the point. We could have done maybe from 3 to 4. I'm sorry, from 1 to 3, duh. And then we could have done from 1.5 to 2.5 and 1.9 to 2.1. And we could have shrunk in and on it that way. And you'll do some of those exercises and see how you approach it. In the end, it's always going to be the same result. So, and another little friendly reminder, if you're given a position function, the average rate of change of the object is the average velocity. So if we have how far a car has traveled over a specific amount of time, and we find the slope of the line connecting 2 points, we're seeing how fast that car traveled on average. If we want to know what happened in an instant in time, that would be the slope of the tangent line at that point. So the instantaneous rate of change, or the instantaneous velocity at a point, is just the slope of the line tangent to the curve. So when you approach these problems, keep that in mind. Nothing changes. They're just adding words to them. All right. Have a good day.